So first of all, I would like to thank the organizers. It's really a huge honor for me to be able to give a talk here at this conference in honor of Jean-Pierre. So what I will talk about is the hyperbolicity of hypersurfaces. So let me just give the context. So if so take X, smooth projective variety over C. And also it has been used in the previous talk. I will just recall a definition. I will say that X is hyperbolic if there exists no entire curve from C into X. So here, to be precise, I should say this is the definition of Brody hyperbolicity. And but for projective varieties, this is a more usual definition of Kobayashi hyperbolicity. So in dimension 1, the situation is very clear and well known, because a curve will be hyperbolic if and only if its genus is bigger than 2. However, in higher dimension, the situation is much more complicated, and it is expected that the hyperbolicity properties of varieties are closely related to the positivity property of its canonical bundle. So this is the content of the green conjecture. This is what I will talk about today. And so what I will talk about is the following conjecture. So it was a conjecture, but now it's a theorem. So Kobayashi in the 70s. Which says that if H in Pn is a general hypersurface sufficiently high degree, then H should be hyperbolic. So here, general, by general, I mean that it should be true for a Zariski open subset in the parameter space, which here is just polynomials of some given degree. And so Kobayashi made this conjecture in the 70s, and since then, many mathematicians have contributed to this problem. Quite a few of them are actually here in the today, and I will so briefly recall the history of this problem. And okay, so for n equals 2, as I said, it's very simple, because if you take a curve in P2, then X is hyperbolic if and only if the genus of X is bigger than 2, if and only if the degree of X is bigger than 4. And so the conjecture is obviously true. And so in higher dimensions, what people first did, they first constructed examples of hyperbolic hypersurfaces. And so I think the very first example is an example due to examples is an example due to Brody and Green, which was a hypersurface in P3 defined by the equations x0 to the power 2d plus x3 to the power 2d plus a x0 x1 dd plus b x0 x2 dd for general a and b complex numbers, and for d, I think bigger than 25. Anyways, it's a deformation of a Fermat hypersurface. And after that, many other people did constructed examples. So let me just name a few, but I will certainly miss many of them is, so I'd like to say Nadel, for instance, De Mailly and El Ghoul, Zeidenberg, Masuda and Noguchi, Duval, and so on. So really, there is a lot of examples. But I should mention that you cannot deduce this general statement from just one example, because it is not known if hyperbolicity is a Zariski open condition. It is known that it is open in the Euclidean topology, but it is not known if it's open in the Zariski topology. So this will come back later. And so for n equals 3, the first proof of this general conjecture were given by Macquillan for d bigger than 35, and by De Mailly and El Ghoul for d bigger than 21, and later refined by Pound for d bigger than 18. Okay. So for in the higher dimensional case, what first happened is that the algebraic analog of this conjecture was established. So it is conjectured that a hyperbolic, that a variety is hyperbolic if and only if all of its subvarieties are of general type. And so this was established by the work of Clements, Hein, and Voisin, later refined by Pacienza. And for the general situation for this problem here, the first step for a general proof was taken by Hsu in 2004, who outlined a strategy to prove this conjecture, so in any dimension. So this strategy was then implemented effectively by Di Verio, Merkel, and Rousseau. So there has been many other work, but I don't state them, who proved algebraic degeneracy of entire curve in general hypersurfaces of degree d bigger than 2 to the power n minus 1 to the power 5. So with an explicit bound on the degree. And this actually allowed Di Verio and Trapani to give a proof of the Kobayashi conjecture in dimension 4. And also building on some previous results of Voisin. And this bound has then since then been improved by several people, so by Bergzy, also De Mailly, and Darondeau. And I think the best bound today is due to Darondeau, and it's d bigger than 5n squared to the power times n to the power n. So the exact value of the bound is not very important, but I should mention that this is very far from the expected bound, which should be linear in n, and it should be actually 2n minus 1, or at least one can hope this to be true. And so the final step for this conjecture was made by Hsu actually in 2015. So in a paper published in 2015, and the pre-publication was available in 2012, where he completed his strategy, and he provided the details of his strategy, and thus completed this proof for any n and for any d large enough. Okay. So before I continue, I should also mention that De Mailly developed a very different approach based on his work on the Green-Griffiths-Lang conjecture. So my contribution here is basically to have another proof of this result. So I just write it here. So it was in 2016, and the proof was not effective on D. Shortly after I made this result available on the archive, Yadeng, which is a student of Demailly, made it effective. So the reason is here there were 2 points where I lost effectivity in the proof, and those 2 points were then made effective by Yadeng shortly after. So 2016 made them effective. And therefore obtained the bound. What the bound is, I think, something like D bigger than n to the power 2n plus 6. Okay. So it's rather again a very huge bound, somehow of the same nature than the best bound known for algebraic degeneracy. Okay, and I should, to conclude, I should mention that this proof was actually motivated by another problem, which is a conjecture of the bar. So I don't have time to explain this, but the bar conjectures that the general complete intersection of a high codimension and high degree should have ample cotangent bundle. So I did quite. I was working on that, and quite recently, in 2015, this conjecture was proved independently by Songyan Xie and by Darondo and myself. And so the ideas in those proofs are the one who led to this to the work I will describe today. And so just to come back to what I said about the examples, let me state that the general strategy of the proof is the following. General strategy is to construct one example of a hypersurface satisfying a stronger property, so a property which is strictly stronger than hyperbolicity, but which is Zariski open. Property. And so then, when you have this stronger property, you can just deduce the entire statement just from the construction from one example. And this is what I will try to explain today. So what this property is and what the example is. And so to do so, this is based on the theory of jet differential equations. So I should equations. And so the first, I think, result motivating those jet differential equations, which is now very classical, but I should state it anyways. And I think it should be attributed to Noguchi, is that if A is ample on X, and then for any entire curve from C to X, and for any omega symmetric differential form twisted by A minus 1, the pullback of the form under F should be equal to 0. So this tells you that symmetric forms give constraints on the existence of entire curves. So that's very good. And for instance, if you show that the cotangent bundle is ample, then you would the variety would be hyperbolic, and it just turns out that the ampleness of the cotangent bundle is a Zariski open property. But the problem is that for hypersurface in Pn, you actually never have symmetric differential forms, except in the case where you are considering curves. And so this leads to considering higher order jet spaces and higher order jet differential equations. So and so I will just recall what the higher order jet spaces are. So for any k bigger than 1, you can construct the jet space associated to of order k of x, which will just be as a set of all germs, of all k jets of germs of function from c into x, where I say that f is equivalent to g if fp of 0 is equal to gp of 0 for any 0 between p and k. And so this gives you a C fiber bundle. So this is a C and K fiber bundle, which for k is equal to 1 is just, of course, a tangent space. And to see that it's a C and K fiber bundle, see it very easily by taking coordinates on x. And then if you have a jet given by, written in those coordinates as this, then the order jet of this will just be given by f1 prime, fn prime, f1 differentiated k times, fn differentiated k times, and everything evaluated at 0. And so you see that you have n times k complex numbers. So there are, say, two natural actions on the jet spaces. So there is a C star action, and there is another action. And I won't talk about the C star action because I don't have that much time. And what I will do, I will follow the ideas of de Mailly and the construction of de Mailly, and consider the action of the following group of reparametrization of jets, which is just a set, so of say phi from 0, C0 to C0 by holomorphism, jets of biholomorphism, where you mod by t to the power k plus 1. So you just take the first k jets, and you can see this as just a set of function of this form here. Where you mod out by t k plus 1. And so this group naturally acts on jk of x just by reparametrization. And so the action is given by as follows. So if you have a k jet f and a phi in this group here, you just look at the k jet of f composed with phi. So I should say that this is actually something quite natural to do, because if you are studying some hyperbolicity properties, you're actually not interested in the way your entire curves are parametrized, but just by the image of the entire curve. So it really makes sense to look at this action by reparametrization. And so for what you can define then is you can define some vector bundles which will, so the vector bundle of jet differential equations, which will be some invariant function on this space here, invariant under this group k. So for any u in x, you can define an open subset. You can define EKM of omega x of u, which is the set of all p in O pk minus 1 of u, such that p of phi times fk is equal to phi prime of 0 to the power m times p of fk for any phi in a gk and for any k jets f. Okay, in where it makes sense. And so these bundles were introduced by de Mailly, and so you can think of them as some higher order generalization of symmetric powers. And so it's actually a vector bundle. And just to give some example, for k is equal to 1, then you have that those bundles are just the symmetric powers of degree m of the cotangent bundle. And for k bigger than 1, the situation is actually much more complicated, but I can at least give you an example which will be important. This, for instance, equation here, which is some which is a Wronskian equation. So here I take the coordinates induced here to define this, and this will be some actually some jet of some jet differential of order 2 and degree 3 over some open subset U where I took some coordinates. And so the the important result concerning those bundles is a generalization of this one here, and it's the following theorem, which tells you that, which is due to Green-Griffiths, Hsu and Young, and de Mailly, which tells you that if is ample on X, and then for any f from C to X, and for any element P, a global section of this bundle here, twisted by some negative power of this ample line bundle, the pullback of P of f is equal to 0. So this tells you that if you have some global jet differential equations which happen to finish along some ample divisors, so of course is very important, then you will have some higher order obstruction to the existence of entire curves. And so it is actually rather natural to try to look at the quotient of this space by this group, but it turns out that this group here is non-reductive, so you don't really know how to construct this quotient immediately. But what you can do, and so which was again so what you can do is to you can actually make some sort of a jet tower. So this sort of construction is actually somehow quite classical, but was used for very different purposes. And so it is in the work of again de Mailly, where this construction was used to study hyperbolicity properties. And so what you can the construction is the following. So you have for each k, you have a sequence of spaces like this, which start with x. Each one of these spaces is a projectivization of some vector bundle on the previous one. And the first one is actually just the projectivization of the cotangent bundle. And so because each one is a projectivization of some vector bundle, each one comes with a tautological line bundle here. Like this. And what happens is that, in fact, inside each one of those spaces, you have an open subset, which is which I will denote x car regular, which can be identified with the quotient of some subset of the jet space under this group action here. And so just I should say that this space here is a space of regular jets of fk with f prime of 0 is different from 0. Okay. So what the really difficult part here is to the difficult part of this construction here is to understand actually what happens on the complement of this open subset here. And so also I should mention that the construction is made so that every curve, entire curve, and in the X3, actually every map from a Riemann surface to X can be lifted to each of those jet spaces. So you can really think of this as some compactification of a quotient of this jet space under this action. And so an important theorem, which is due to de Mailly, is that if you take the tautological line bundle on xk, and if you push it down onto this space here, you will exactly get those vector bundles there. So I should have given a name to this. I will call it pi k star of oxk of m is equal to e k m omega x. And so what you get from this in particular is that for any ample on x, and for any, so here I will give a slight generalization from the natural statements that you would get here, just because it's a bit more convenient. AK in n, and for any omega in h0 of xk, oxk, a1, ak, twisted by pi k star of I minus 1, and for any entire curve f from C into x, the case order lift of this curve here will have to lie in the 0 locus of the section here. Is included in this set here. So what you see from this is that you can, to some extent, study hyperbolicity properties with by studying the positivity properties of some line bundle, which is, so this line bundle is just the natural linear combination of all those line bundles here. And so you can, for instance, hope if you're that, for instance, if this line bundle here were to be ample, then the variety x would be hyperbolic. So this is not exactly what I need, but you can make a slight modification of this this thing as follows. And so I should make a little remark. The remark is that if you lift any entire non-constant, I should have said non-constant, of course, any non-constant entire curve here, the image will intersect this regular part. It cannot lie in the complement of this regular the set of regular jets. So for any f from C to x, if one denotes xk singular to be the complement of this open subset regular, then f of C is not included in xk singular. So what this tells you is that when you're studying the positivity of this line bundle here, what actually happens above this set xk singular, which is actually a divisor, I should have mentioned it, this is actually a divisor in xk, is not really that important. And as a corollary of this and of the previous statement here, you can see that if you have some xk twiddle to mu to xk, say some birational map, some birational morphism, and if you have some some effective divisor in x k hat, which is contained, E is contained in mu k minus 1 of xk singular. If if it happens that mu star of oxk a1 ak times O minus E is ample, then this will imply then x is hyperbolic. And so this is exactly the sort of property I will need for to have a stronger property that is Zariski open. It will be a birational modification of xk and some ampleness property on this birational modification. And it will work because ampleness is an open, a Zariski open condition. So this is what gives you the Zariski openness. And okay. And so now I will try to briefly explain, well, what is actually this birational modification. And this is based on some Wronskian construction, actually. So Wronskians are actually very, have been used in many ways in these sort of problems. But so here, this construction is actually somehow slightly different. So I will take some very ample line bundle on X, and I will take some S0 Sk in some global section of this line bundle. And what you can associate to this is some section, some Wronskian of this section, which is defined locally as follows. Just you take S0 Sk in the first line, then you take ds0 dsk in the second line, and you take dk S0 dk sk in the last line. And where this, for any holomorphic function on some open subset of X, this differential dp of S is defined as a holomorphic function on the jet space, which is defined the only reasonable way, which is the following. S composed with F differentiated P times evaluated on 0. So this is actually, you can see that this actually gives you some holomorphic function on the jet space. And it turns out that if you make the computation, you will see that it is actually invariant under the GK action. So it will give you some invariant jet differential. And moreover, if you look at how the transition map works, you will see that this actually defines a global section of some line bundle, which some vector bundle, which is actually this one, omega x, twisted by a to the power k plus 1. Okay. So I should say here that in the case of curves, this construction is actually rather is well known, and I don't know to which extent it's classical, but it's certainly well known. And for instance, it was used in some related problems by Noguchi in some work on the Nevandina-Cartan theory over function fields. And so it's somehow a higher dimensional generalization. And so what you have here is a global section of this. And of course, you cannot obtain some hyperbolicity statement from this, because here the twist is a positive twist, of course. So you can't a priori do anything with that. But what you have is that this, in view of de Mailly's theorem, is the same thing as this space here, k plus 1. And so what this actually defines you, this defines you a map from the k plus 1 exterior power of the global section of XA to this space here. K plus 1. Okay. And what you can do is you can look at, so it gives you many section of those tautological line bundle. And what you can do is just to look at the ideal sheaf generated by those sections. So you can define WA, the ideal sheaf associated, so maybe I should call this W, associated to the image of W. So this gives you some ideal sheaf on XK, and what you can actually see, so it's a fact, is that under the hypothesis that A is very ample, you will have a chain of inclusions this way. This will eventually stabilize to some thing which is independent of A. And here is the first point where Yadeng made the argument effective. Yadeng actually showed that this is exactly the ideal sheaf associated to A to the power k. So this is due to Deng. And which is actually quite important in the proof, well, to make it effective at least. And the second is that the support of this ideal is supported actually on the set of xk the locus of singular jets. And so by what I said just before, what you can actually do is just to consider the blow up to be the blow up of xk along this ideal sheaf here, which is above xk, and I will call this map nu k. And I will denote the exceptional divisor by f for some reason. Okay, so you could also take a log resolution of this ideal sheaf if you want. It doesn't really matter. And what this corollary I just erased tells you is that if you consider the following property, star, which I call star, which means that there exists A1, AK, and Q in N such that mu k star of OXK A1 AK twisted by OXK hat minus QF is ample. So this property now satisfies two things. First, if X satisfies star, implies that X is hyperbolic. And the second thing is that star is a Zariski open property. And so Zariski openness just follows from the ampleness, so Zariski openness of ampleness, actually. So there's really nothing mysterious here. And so in the few minutes I have left, I would like to tell you what is the example that satisfies a star and which can be used to prove this statement on the hyperbolicity of general hypersurfaces. And those examples are actually very similar to the one constructed as examples of hyperbolic hypersurfaces. And so I will consider the following thing. So here I will take X equal to Pn. And so I should mention that really the proof doesn't rely at any moment on the fact that the ambient space is Pn. So it just take it here to simplify, but it would give you actually immediately the statement for any sufficiently ample hypersurface in any variety. And so I will consider jets of order k bigger than n-1. So this is a necessity because of some work of Diverio, who showed that for hypersurface in Pn you can never have jets of order less than the dimension of the hypersurface. And the equations I will consider are the following. So I0 plus In equals delta to A I0 In x0 to the power r plus k I0 times x n to the power r plus k n. It's somehow a deformation of a Fermat hypersurface. So it's which I will write as follows, just in multi-index notations to the power r I. And so here, these are of degree, some polynomial of degree epsilon, which you should think of some small polynomials. And so the total thing is of degree epsilon plus r plus k times delta. And it's actually exactly for those degrees that you can prove this statement. And and you can actually easily see that you can reach every sufficiently high degree as in this way. And so, so now you can ask why do those hypersurfaces have anything to do with this condition? So I will try to explain this quickly. So the main idea, is that if you look at the equations in this way, and you differentiate the equation, so locally, so here I just, this is only local, I write it this way just to simplify the presentation. But you see that when you differentiate something like this, what can happen is at most you can lose a power 1 in the exponent here. And so if you do the computations, you will see that this is of the form a twiddle 1 x to the power a plus k minus 1I, and up to jets of order k, this will be equal to sum of ai k twiddle x to the power r plus k minus k I. And so if you rewrite this slightly differently, you can rewrite this as alpha I 0 times x to the power ri. And here you can rewrite this as alpha I1 x to the power ri. This as alpha ik x to the power ri. And here comes the trick. The real trick is to make the change of variables ti to be xi to the power r, and you will land with some equations like this, t to the power I. And so what you have here is the equations of the higher order jet space of the hypersurface defined by f. So here we'll set HA to be the hypersurface defined by these polynomials. And what you actually have here is, if you think of it, some equations for some universal complete intersection of codimension k plus 1 and multi-degree delta. Just the delta is the of all those indices. So we just really briefly state this. So you have this universal complete intersection is most naturally parametrized by a subspace of some Grassmannian Pn O delta times Pn, where the condition is that P of t is equal to 0 for every P in delta. So really, this is just a natural way to define the universal complete intersection parametrizing k plus 1, complete intersection of codimension k plus 1 and multi-degree delta delta. And what the sketch, the really brief sketch of the proof is, to prove that these hypersurfaces satisfy the condition star, is to show that for A general, you will have so here you have just your hypersurface HA. Here you have the case ordered jet space of A, and here you have this blow up. And what these equations will actually tell you is that here you have a rational map which goes to Y. But it's only a rational map. It's never an actual morphism. But for general A, if you blow it up, blowing up this Wronskian ideal sheaf, you will actually get a morphism. And the second thing, just 1 minute, and I will conclude. The second thing is that here you have some morphism to the Grassmannian, and here you have some morphism to Pn, Q1 and Q2, and here you have some tautological line bundle Q, and here you have some, which is the Plücker line bundle, and here you have some tautological line bundle OPN of 1. And what happens is that you have this equation here, is that the pullback of some power of Q times OPN of -1 is actually equal to, so I will write just briefly what it is. And so here I will say something minus R times OHAK hat minus MF. And so here you have a number which is completely explicit, but it's a positive number. And the point is that if R is big enough, this here will be negative. So if R is strictly bigger than star, which I did not define. And then what this tells you is that, so you can think of global section of this bundle as jet differential equations on HA, which give you constraints on the entire curve. And so every global section of this bundle here will be pulled back to some jet differential equation. And the point is that this map here, under the hypothesis I am under, is that this map is actually generically finite. So what this tells you is that the pullback of this line bundle Q is actually nef and big. So it will actually have many global sections. So this bundle here will actually have many global sections if M is big enough. And moreover, you can actually control the geometry of the obtained sections by studying the geometry of Y. And so this way, you will somehow end up proving that this line here is nef, and from this, you will deduce condition star by some standard arguments. And so I will stop here. Thank you very much.